Okay, so we have the Large Hadron Collider, which large is large, it's 27 kilometers circumference. It's a collider, it collides particles called protons, which are part of the family of hadrons. So those are the three elements, LHC, Large Hadron Collider.
Right.
Now to bend the protons around the ring requires magnetic field. Charged particle like a proton with positive charge. It goes in a magnetic field, north to south. The proton will be bent in a particular way, clockwise, say. Let's say the protons go clockwise round the ring. The previous collider we had here was a large electron-positron collider. Now electrons have negative charge.
Right.
And their antiparticles, positrons, because they're antiparticles, have positive charge. Now if you have a magnetic field,
yes,
dipole magnetic field, two poles, electrons would go, well, they've got opposite charge, so they'll go that way actually. They'll go that way, but the positrons, if they come in the opposite direction, they're actually bent the same way as the electrons are bending. So you only need one magnet. So you have your bunches of electrons going one way and your bunches of positrons going the other way. And you can keep them just sort of separate from each other and just make them collide at given points where you have your detectors.
Okay.
So that's what they did before. Now the problem with the Large Hadron Collider is that we don't make enough antiprotons to be able to have antiprotons and protons going in opposite directions. Although that's what happened in fact with the experiments that Olivia did back in the 1980s. It would be nice to do that, but you've got to make lots and lots of antiprotons to do that, and it's difficult to make antiprotons already. So it's easier to have protons going one way and protons going the other way. But when they get to the magnetic field, if you just had one magnetic field, the protons would go that way, but the ones coming the other way would be bent the wrong way.
Right.
So they'd be trying to go anti-clockwise, or they'd be trying to go right when the other ones are trying to go left at the bend. So what we have here are very special dipole magnets, which actually have two sets of magnetic fields in them. So there's the two tubes. So within one structure there are two tubes, protons going one way, protons coming the other way. And in one tube you've got the magnetic field north-south like that, and in the other tube it's the other way around. And when we go inside we'll actually see cross-sections of real magnets. But the ring itself, the 27 kilometers, it's got 1,232 of these long blue tubes in, and which are the dipole magnets, the bending magnets. You'll also hear about quadrupole magnets, which means they've got four poles, two north, two souths, and those tend to focus the beam like lenses do. So it's almost like an optics experiment that you do at school with a bench.
Magnets.
Yeah, that you do with magnets. And then they have, so the focusing magnets try to keep the particle beams focused, obviously, but then you have what you call corrector magnets because the magnetic fields aren't perfect. Nothing is perfect, but to try and get as near to perfection as possible, you make corrections just as you would optically. You make collection probably with your camera. There are lenses that. So there are sextupoles and octupoles and all sorts of poles.
To fiddle and get it to all work right.
Yes. So there are. So I think the total number of magnets is something like 8,000.
Wow.
Yes. And they are all.
So it's almost 8 times as many as the basic number.
Some of them are quite little ones, not these big 15-meter ones.
Right.
And they are all superconducting, which means that they are operating at very low temperature.
So but this is an actual one.
It's part of a prototype. Electrical conductivity.
Right. So the beam
went apart and then it went back together again.